sensor networks and related sensing and actuation technologies. His work integrates applied mechanics, smart materials, and device-level engineering, and in this session he's going to discuss the development of airborne piezoelectric micromachined ultrasonic transducer phased arrays for three-dimensional spatial range detection. So please welcome Professor Wu.
Thank you for the introduction. Yeah, I think according to the schedule, I have -5 minutes, so I'm going to make my presentation as short as possible so we can catch up the lunch. Okay, so this morning we already have Professor Zhang's keynote speech. He covered the whole piezoelectric material technology and the advancement in past 20-30 years. So I think I can completely skip the piezoelectric material introduction, and my presentation is all about the application side. We are using piezo material on the airborne ultrasonic ranging sensing application. Okay, so this is our line, and for the market, for the most mature ultrasonic application, I should say the biggest market is actually on the medical ultrasound area, and the frequency range is using is like above megahertz. So it can do medical imaging that's already mature in every hospital. A lot of many of you probably already have experience on doing this kind of ultrasonic medical imaging. And for the other side, we say the airborne ultrasonic sensors, the most popular application would be automotive area, the parking sensors. So like if you buy a Mercedes or BMW, typically nowadays the car will equip with 8 to 12 ultrasonic sensor on it for parking assistance. And we also sometimes say the ADAS, the driving assistance system. And the penetration of this kind of ultrasonic parking sensor in Asian market is almost 100%. In European market also around 70 to 80. But in North America, that's one of the exceptions because people there tend to like visual-based sensors, and they are regulation for car to have the visual camera installed on every car when you are baking. And so I just mentioned for the parking sensor for automotive applications for the latest multi-focus, I think there's about 500 million pieces installed on car every year from like Bosch or Valeo, the two most leading tier 1 company. And the frequency range is using is typically around 40K, 60K for airborne because it cannot be such high as medical imaging. Although with a higher frequency, the wavelength is shorter, we can have higher resolution. But for such high frequency ultrasound, it's almost impossible. It's almost impossible to transmit in sound because the annihilation is too fast. So for airborne air-coupled ultrasound, typically application frequency is lower than 200 Hz. So like the parking sensor I just mentioned on cars nowadays is typically using 50K to 60K Hertz. Okay, so for this topic, this presentation, actually we are targeting on array ultrasonic sensor, so we can do beam forming. For the ultrasonic sensor on cars today is still a single transducer, but you install many of them. So you cannot do imaging, but you can do quite precise the range measurement. So you can combine with the other sensors, for example, a visual camera to do sensor fusion. And what I would like to make is tiny and also beam forming. One of the target market is actually for the user interface, like the VR headsets or the virtual reality or augmented reality, VR AR headsets. And all of you probably know because sense of the AI advancement in past 3 years, people are now exploring new interface of human and computers. So like the smart glasses or the VR headsets is one of the hottest targets. So last year, like Meta already announced the smart glasses product, and even Ray-Ban also now has smart glasses, smart glasses product. And on this kind of tiny headset, you require to have low power consumption, and it cannot too bulky, and also it can capture your gesture, or also do hand tracking. Of course, conventional sensors like optical, like LiDAR can do it quite well, but it's too power consumption. So power consuming. So we are now exploring the other possibility to using ultrasonic transducer. Okay, so for the beamforming theory, I think I can skip in mathematics. For the design of an array sensor, of course, we would like to have a beamforming with tiny phase difference, so we can control the scanning angle of the array sensors. And also, the other important thing is to control the side lobe. We hope to have all of our array sensor can have a very strong main lobe and small side lobe. So we can do combining a different sensor well without being affected by the side lobes. So according to the design, we can design the optimal distance between the array sensors, and I'm going to move to the fabrication parts. So for our array sensor, we are targeting the sensor is not in really micron size because of air coupled frequency is low. It cannot be too small, or the efficiency is not so good. So our idea is to fabricate a PMOS sensor that's around 1 meter in size. But because of array sensor, we need to make a lot of them. Later on, I will show you we fabricate one with 19 sensor in a single package. But the fabrication platform is developed in my lab for past 20 years. In the very beginning, we use this platform to fabricate energy transformer and then energy harvester. I spent probably more than 10 years working on energy harvester development, and the transducer typically we make is around centimeter in size, so we can have enough power output. So for the although our sensor, our transducer is bigger, but the fabrication process is still quite typical micro fabrication techniques. We are using the photoresist, zinc photoresist, so we can do leave off for the PET with deposit, and the PET layer, the piezoelectric layer, 80 layer we fabricate is using the aerosol deposition method that's also in-house developed. And then we also do like a wet etching to define the final shape, final outline shape. And then we need to do like annealing to activate the piezoelectric layer. And then of course we also need to do polling to activate the piezoelectric property. Okay, so this is the final dimension. The final dimension of our PMOS array is 25 millimeter by 20 millimeter. And this is the aerosol deposition method we developed in my lab. This method is originally invented by a Japanese researcher in ICE around 25 years ago, and we built a machine in my lab by ourselves, and it can grow very dense. I touch it. Sorry. It can grow very dense piezoelectric ceramic film. And the film thickness is around 10 to 20 microns. So, sorry, I don't know. Sorry. Okay. So the thickness we can grow is typically 5 to 12 micron. I got some trouble. So I don't touch it. And the process like we put a powder in the powder chamber, and then we have the outside chamber in vacuum. So we create a huge pressure difference. And the particle typically 1 micron in size, because of pressure difference, it will accelerate and convert into the substrate upside down. And the substrate we are using is stainless steel. It has a lot of advantage. Because I do not have enough time, I don't explain the details. And because of the final velocity, heating the substrate will be above sound velocity, so it can create very dense piezoelectric thin film. Okay, and this is the packaging we design. Of course, for this kind of transducer, packaging design is also very important. We use a PCB, a standard PCB process. On the bottom, on the top layer, the gray portion is our piezoelectric transducer, and then we have some pogo pin, that's a spring-loaded pin to touch the electrode of the buttons button side of the piezoelectric layer. On the top, we of course grow some electrode on it, and then also on the top side, we'll glue the other stainless steel pieces to create an aperture, to design the aperture. So individual piezoelectric transducer is in fixed boundary conjunction, so we can further have a resonant frequency being higher, going to around 50 kilohertz. That's our target design frequency. And on the right hand side, you see a driving board we made by ourselves. We're using a chip that's from anode device. It can generate several channels of sinusoidal sine wave, and we can control the phase difference. And with some operational amplifier, we can also amplify the signal and use that to drive in our piezoelectric transducer. Okay, and also the first thing is like this one. We fabricate 19 piezoelectric transducer on the array, and the first thing we need to measure frequency response. And unfortunately, you can see the curve. We still have difficulty on the uniformity of the transducer, the single transducer we measure. So for example, like the left-hand side, you can see the resonant frequency is away from our design frequency, 60K, by almost 10 kilohertz. And for like, if you want to do beamforming, it's already far away from what we can do because the frequency difference is too large. So in the end, we just can choose some of them that's already good enough and a resonant frequency close enough to do the final verification. Okay, and of course, not only a frequency response, we also need to do the beam pattern measurement of the individual array transducer, and also the beamforming array coupling angle test. So from the right up view graph, we can see if we control the beamforming to be minus 15 and positive 15, we can clearly see the main lobe is moving as we expected, and also 30 degree and 45 degree. And this is the power signal we can get, and this is the L-bone ultrasonic transducer, so you can see the power signal is actually quite strong and quite clear. And from the threshold for signal to noise ratio, we can conclude that the sensor working quite well, and the theoretical range we can reach is around 3 meters. And this is the final calculation. We try to do the beamforming scanning. This is on the transmitting side. For receiving, we're still using a single MEMS microphone. We can already target find a target we set as a plate quite well. And the second correlation demo we test is like we have two obstacle two plates in different distance. So you can see on the right side view graph, we can do already like very similar to medical ultrasound to get the quite clear ultrasonic ranging view graph with depth information on it. Okay, so final conclusion, we have successfully fabricated the array PMOD ultrasonic transducer, and the sound pressure level is quite good, and the maximum detection range, I just say theoretical, we think is can up to 3 meters, but for real experiment, it's about 1.5 meters. But for like a smart glasses application, is already good enough, and the field of view is around 75 degrees. It's already good enough. And starting from next year, we are going to have a new project working from a professor from EE department, computer science department, to explore the like VR, AR headset, real world applications. Okay, thank you very much.
Do we have any questions? I was wondering, what are the fundamental limits in shrinking your device size? What is the current factor that's limiting making your devices smaller?
Yeah, this is a good question. I think the major limitation should be the wavelength of the ultrasonic sound, because we are people using 50K, 60K. If we shrink, it's even smaller, then the frequency should go higher. When the frequency go higher, the attenuation in the air will be stronger. Okay, so this is a good travel. We are still growing at around 60K, but quite the frequency nowadays we are using parking sensor applications.
All right, thank you very much. Shall we thank our speaker once more?
Thank you.